It's down to me to introduce this evening's speaker, Paul Kerr. Now, this is possibly one of the more unusual introductions that I've ever done, and I'm stumbling a little bit. Some of you might have noticed a sort of close family resemblance, and it's fair to say that I've known Paul all of his life, and most of mine. But Paul's come along tonight to talk to you. I won't give his introduction, but to talk about the potential for radical innovation in the wave sector to drive down costs. But what I would say is that Paul's somebody I have observed has been very interested in renewables pretty much all of his life, and I think being in Orkney has shaped that to a very great extent. However, from this Sandy Kerr, I'm going to introduce Paul Kerr, who's the speaker this evening. So, Paul, over to you.
Great. Thank you for such a nice introduction, and thanks everyone for... Sorry.
Just get the screen share online.
Are we good?
Should be it now.
Okay. Good to go. Thank you everyone for coming, especially on such a nice evening like this. So, as Sandy kind of briefly said, I'm going to be talking today about cost reduction and innovation for the wave energy sector. This is based on work that I did during the course of my PhD research, which I just finished at the beginning of this year. So I did that at the University of Edinburgh, and my project was funded by Wave Energy Scotland. So if anyone hasn't heard of them, they're probably the biggest funder of wave energy research and development and demonstration in the UK at the moment. University of Edinburgh is where I carried it out, and the Energy Technology Partnership also sponsored my project. Sorry, I'm going to be clicking through with this and using this for my notes, so bear with me. And I just realised I didn't have it on presenter view yet. Okay, so my background is that I grew up in Orkney. I think that's what kind of instilled in me a real interest in renewable energy. I got to see devices being tested at the EMEC Centre, which at Billy Crew, which is just kind of a short walk from where I live. Also, a funny thing that I dug up was that I did my school history project in second year of secondary school on the history of wind turbines in Orkney, which I think was a bit of a shock to my history teacher. Probably wasn't wanting something that engineering focused. Then went on to study mechanical engineering with renewable energy at the University of Edinburgh until 2019. And then from then until the beginning of this year, I was doing a PhD in wave energy innovation at the University of Edinburgh. This was kind of, it was with the kind of subject areas of innovation in the wave energy sector, and also kind of techno-economics. So just to kind of give you a quick overview of my research areas, this project was, I was doing it both with with the University of Edinburgh as my kind of academic supervisor, was from there, and then Wave Energy Scotland was the industrial partner. And this made it kind of an interesting project because it had two quite distinct different focuses. The first one being looking at wave energy cost reduction pathways and the role that innovation could play in that. So I did that mainly with the University of Edinburgh, and that's what I'm going to be talking about today. And then a second part of my work was about developing assessment processes for an innovative class of conversion technology for wave energy applications, and that was done more with Wave Energy Scotland, kind of more close collaboration with them. And so while this is a really kind of interesting project to do because it had two quite different research areas, I think it also kind of felt like at times that there was, I guess, there were so many kind of interesting kind of ideas from the academic and industrial supervisors coming at me, and it was kind of quite challenging because of that, but I was kind of lucky to have really, really good supervisors as well, so I think that kind of helped me get through it for sure. So just for anyone who, I mean, this will be kind of common knowledge to some of you, but just for a little bit of background on the kind of things that you should kind of know about the wave energy sector if you haven't been following it closely. I think the first thing to say about wave energy is, unlike something like wind, where kind of the horizontal axis 3-blade turbine is kind of ubiquitous now, there are lots and lots of different ways that you could extract wave energy, and correspondingly then lots and lots of different kind of potential wave energy converter designs to do this. So some of these devices probably look familiar to people. So the kind of top left we have the kind of point absorber wave energy converter that is kind of like the core power device. That surge type device there, that's like the Oyster, which was deployed at Billy Crew. This attenuator device, that is the kind of working principle of Polamis, and that rotating mass device is like the Penguin device, which is also tested in Orkney. So I think what I kind of want to highlight here is that there are many different potential wave energy technologies that could be developed, and they have very different kind of characteristics. The second thing is that wave energy is yet to have kind of progressed from the research and development and demonstration phases to actual commercial deployment. That's the reason why you're not seeing kind of farms of wave energy converters out there at the moment. Unfortunately, they don't exist yet. So kind of correspondingly, over the last 20 years or so, only about 30 megawatts of wave energy has actually gone into the water, and most of that's been kind of single device demonstrations, with the exception of a couple of projects. However, the resource exists for hundreds of gigawatts of wave energy worldwide, so there is a significant resource out there, and especially in a European context. We have a kind of particularly good wave resource. You could get kind of 20 plus gigawatts is the kind of numbers that are thrown around for the UK resource. So it could be a significant source of electricity generation. And I think some of the kind of key challenges that the wave energy sector faces is kind of issues around the high ratio of capital costs to absorbed wave energy, and also reliability, just surviving those kind of harsh conditions that you get in a marine environment. So that's the kind of preamble out of the way. So the kind of rest of this presentation, I'm going to start by talking about renewable energy cost reductions in general, and then I'm going to talk about how I applied this to my work, looking at the potential cost reduction for wave energy, for the wave energy sector. I'll then kind of talk about briefly the findings from my research, and then at the end, if anyone wants to, I'm happy to take some questions. Okay, so when we're thinking about cost reduction for renewable energy technologies in the energy innovation literature, it's generally divided into two different categories. So the first category are incremental cost reductions. So these are the kind of small improvements that happen alongside the deployment of a existing commercial technology. And these individual improvements might be small, but over time they kind of aggregate and can be quite significant. So if we think about a kind of example from the automotive sector, the internal combustion engine, it's a technology that's been around for like 100 years now, but every year it's kind of become slightly more efficient. So in the last 50 years, it's around about come down in half the amount of fuel that's needed per kilometre in an internal combustion engine. So those are small individual improvements, but over time they aggregate to be significant. The other kind of cost reductions we have are ones that come from innovation. So this is when a new technology is developed that strongly deviates from what already exists, and this can lead to a kind of step change in performance. So if we're thinking about the energy sector, that's different ways of storing, harvesting, or converting energy. And generally, these are not the results of kind of increases in deployment of an existing technology. It's something that stems from research and development that can be implemented into a new technology. So if we think about the automotive example again, the kind of transition from the internal combustion engine to battery electric vehicles, that's a kind of step change innovation. It's multiple times more efficient compared to the kind of small improvements that we've seen with the internal combustion engine over a very long period of time. Sorry, I'm just getting used to the clicker. So I'm going to start off by talking about the cost reductions that you get alongside deployment. And I think an interesting kind of question to start off with when we're thinking about this is why do we even bother subsidising the deployment of high-cost, early-stage renewable energy technologies? I think one of these reasons is quite obvious. I mean, the alternative is polluting fossil fuels. And we want some way of kind of levelling the playing field between those two technologies, so a subsidy helps to do that. The other reason is that as we deploy more of a initially high-cost, early-stage renewable energy technology, we expect cost reductions to occur as a result of this deployment. And that has been true for most of the renewable energy technologies that we've deployed, and it's been the kind of main factor in their cost reduction in the last few decades. So these deployment-related cost reductions can come from lots of different sources. So some of the important ones here, learning by doing. So simply, as you manufacture more of a technology, the processes become improved and the cost comes down. So an example with solar PV is incrementally less silicon is used in the manufacturing of solar cells. The wafers in the solar cells are sliced thinner and thinner as the manufacturing process is improved. And nowadays they use about a third of the silicon that they did 15 years ago. And that's been a kind of incremental process. Learning by using, as technologies are deployed, we learn about how to operate them better, so developing better operations and maintenance regimes and better installation methods. Economies of scale and volume, obviously. So as technologies like wind have been deployed, they've slowly increased in scale. And that's allowed them to achieve kind of higher capacity factors, which has reduced their cost of electricity. Economies of volume, simply producing more of something allows you to have kind of bigger facilities, reducing overheads and reducing costs. And then also as technology is demonstrated, its reliability is demonstrated, it becomes a less kind of risky proposition for investment. So it's easier the kind of risk premium charged on borrowing to finance a renewable energy project comes down, which is really important for renewable energy projects. Yeah, so to illustrate how important these deployment-related cost reductions have been for renewable energy, I'm just going to kind of show you the progression of some of the key renewable energy technologies in the UK. So the data I'm going to show you on this slide is from the International Renewable Energy Agency Energy Cost Database. It's UK data. What we have on this plot here is on the y-axis we have levelized cost of electricity. So just think of that as the kind of through-life cost of electricity generation from these different technologies. And you can see on the x-axis it's from 2010 until 2022. The kind of grey range that isn't showing up very well here, but it's the range between these two lines is the approximate UK gas generation marginal cost range. As we know, the cost of gas goes up and down, but kind of historically, at least until the last couple of years with the energy crisis, it's basically kind of bounced around between these two lines. And that's important because most of the time the wholesale electricity price is set by the price of gas. Oops. So we can see if we go back to 2010, onshore wind is kind of about the kind of top of that cost range of gas, but the other technologies, offshore wind and solar, they're miles above that. And if you didn't expect there to be cost reductions that came alongside deployment, you'd have a very hard time kind of justifying subsidizing the deployment of these technologies. The thing is, luckily, they have come down in cost a lot as they've been rolled out. Indeed, solar photovoltaic has fallen by almost 90% over this time period in cost, and onshore and offshore wind both by a little under 70%. So you can see that's a kind of massive cost reduction, and indeed these mature renewable energy technologies, they're now down at the same or even below the kind of cost range of the fossil fuel alternative in the UK, which is kind of quite remarkable development, I think. One thing I wanted to point out, though, is that cost reduction doesn't come for free. Subsidy is required for the early phases of deployment. So solar PV would never have been deployed. It would have never achieved those cost reductions if it hadn't been subsidized. And if you don't subsidize the deployment of these higher cost technologies in their early stages, there's a kind of insurmountable difference between that technology and the fossil fuel incumbent. And you could just be locked into the kind of more mature option forever. And this subsidy can be quite a lot. So Germany is the kind of famous example. They spent around 100 billion euros on subsidizing the deployment of solar PV. And that's really because they started subsidizing solar at a very, very high cost of electricity in a kind of uncapped way, so as many people could apply for it as they wanted to, and they did. But I think we should also be kind of thankful that Germany did that, because they subsidized the really expensive bit of the cost reduction trajectory, and we're all benefiting from that now. And as I said, the case is now that new wind and solar are effectively subsidy-free. The support that's offered by the governments in the UK now is more of a way of kind of stabilizing their revenue and making the projects more investable, rather than actually giving them a subsidy over the cost of fossil fuel generation. A quite nice kind of status on this recently was that in 2023 we saw the second highest deployment of rooftop solar that we ever had in the UK, and that was only beaten out by 2011. The thing is, in 2011 you got a feed-in tariff of almost 600 euros per megawatt hour to put solar on your roof, and nowadays you don't get anything at all. So you can see that there's almost the same demand for this technology, even though there's no subsidy being offered for it anymore. Yeah, so I hope you're all kind of convinced now that of the importance of deployment-related cost reductions. But I think a question that you might be wondering is if they happen in a predictable way. And the answer is that yes, they do to an extent. There's a relationship called the experience curve, which some of you may have heard of before because it shows up in quite a lot of different technologies. And it's a way of measuring historic rates of deployment-related cost reduction and then extrapolating these into the future to see where a technology's cost might go. Yeah, and the experience curve is used in some way in a lot of different cost forecasts for energy technology cost reductions. So both in established sectors like wind and solar, but then also by organisations like the Offshore Renewable Energy Catapult if they're looking at where offshore renewable energy technologies might go in the future. And it's what I used when I was looking at the potential cost reduction pathways for the wave energy sector. Yeah, so to demonstrate this experience curve relationship, what I've done is I've plotted levelized cost of electricity data again for solar photovoltaic and onshore wind. This time it's global data, it's not just for the UK. And on the x-axis, instead of cumulative deployed capacity, instead of time, we have cumulative deployed capacity. So what you can see is there's, especially with solar, there's this kind of rapid initial fall in costs in the early stages of deployment, and then it kind of begins to level out as more and more of the technology is deployed. And you'd see a similar thing for wind if we went back earlier in the time series to where it was at an earlier stage of deployment. It's just in 2010 there was a lot more wind deployed than there was solar photovoltaic. The thing is, it's not clear exactly if there is a kind of trend in this cost reduction or not, or a kind of regular, predictable rate of cost reduction. It just looks like a kind of slope. Whoops. However, if you transform this data onto logarithmic axes, so we've got on the y-axis the logarithm of the cost, and on the x-axis the logarithm of the deployed capacity, what you can see is actually quite a linear relationship between deployment and costs. And you can, you can draw a trend line through this using a regression analysis. And this is essentially the experience curve relationship. This describes a constant percentage cost reduction that occurs alongside a percentage increase in deployment. And it's described by something called the learning rate. And the learning rate describes the percentage cost reduction you get each time the deployment of a technology is doubled. So for solar photovoltaic, for the last kind of 20 or 30 years, it's basically followed this relationship. Every time its deployment is doubled, it comes down in cost by about 25% in terms of cost of electricity. I think the other thing that you can kind of see from this as well is that if you extrapolate this relationship into the future, you can make a prediction about where the cost of your technology will be at some future level of deployment. And that's the kind of the power of the experience curve relationship. It's looking at a kind of long-term trend in the technology's costs and seeing where it might go in the future. I think that's another thing to kind of point out as well, is that it is a long-term trend. You'd expect kind of fluctuations in the short term. Indeed, you can see with onshore wind here, there'll be a bit more fluctuation around a trend line that you drew through it. But yeah, the benefit of it is looking at what could happen in the long term. Sorry, it's not, clicker's not working. Oh yeah, thanks, sorry. Yeah, so to kind of illustrate the predictive power of the experience curve, what I'm showing you here is a figure from a report from the International Energy Agency that was produced in the late 90s. And what you can see here is they've plotted an experience curve for solar photovoltaic up until 1997, and then they've projected that relationship out into the future, and that's to make a prediction about when they thought solar photovoltaic might be cost competitive with a fossil fuel alternative. And you can see they've also plotted these dotted lines here, and those show those are based on the confidence intervals of the regression that they did, which gives a kind of range in terms of where they think it will break even with a fossil fuel alternative. And the nice thing that you can see about this is that you can also then look at the amount of subsidy that will be required to carry out that deployment above the cost of that other technology, which is a really kind of useful thing to be able to estimate. And the other thing I kind of realized when I was looking at this is that, well, solar photovoltaic is now, it is competitive with fossil fuel alternatives. So I looked at the price level that they had set this at, and it turns out that this is the level of deployment that solar kind of met that price level at. So what you can see is it's kind of within the kind of range of the confidence interval that they projected like 20 years ago, which I think is quite incredible that they made a kind of projection over that kind of period of time, and it's fairly accurate. It just kind of shows that solar has continued to go down that cost reduction pathway quite consistently. Yeah, and just to kind of show you some other examples, I mean, we've seen experience curves not only for solar photovoltaic and onshore wind. There's concentrating solar power and offshore wind, as well as those two technologies. In terms of energy storage, you see it in different kinds of battery technologies. So these are experience curves for different battery chemistries from the from a journal article in Nature Energy. And actually the first demonstration of experience curves in a manufacturing sector was in the aviation sector almost 100 years ago, where they observed reductions in the cost of producing each additional aircraft unit. As I said, many different technologies have demonstrated experience curves. However, the kind of slope of these cost reductions have been different. So the technology that's really had the kind of highest learning rate is solar PV. So as I said, 25% cost reduction each time its deployed capacity is doubled. Onshore wind has been about 15%, which is also kind of relatively high, and batteries for electric vehicles also about 15%. An interesting thing to note is that nuclear energy has not kind of shown this learning behavior at all. Its cost hasn't come down at all in the last kind of several decades, especially in Western countries. And I think the other thing to kind of point out with the experience curve and learning rates is we don't know what the learning rate will be before we start deploying a technology. However, as I'm going to kind of show you on the next slide, there are some kind of general principles about which technologies may experience fast or slow learning rates. So yeah, this is a figure that I took from a journal article that reviewed kind of about 200 different studies on experience curves and learning rates in energy technologies. And they divided the technologies that they looked at into ones that had fast learning rates, so fast cost reduction alongside deployment, medium learning rates, which are the blue ones, alongside deployment, and then really slow learning rates or no learning at all, which are those red ones. And you can see they've plotted them on two axes, which are firstly the degree of design complexity on the y-axis. So basically the extremely complex technologies with lots and lots of different interacting parts, they learn slowly. And then the technologies and then the other axis, is the level of standardization. So the kind of highly standardized technologies, they're the same wherever you deploy them. They seem to learn at a high rate, whereas the really kind of customized technologies that are different when they're deployed in different applications, they don't learn as quickly. So yeah, basically the kind of highly standardized low complexity technologies like solar PV, LEDs, they learn really quickly. The technologies which are very, very complex, need a lot of customization each time they're deployed. The kind of premier example of this is nuclear energy, don't really learn at all. And you have some other technologies like wind energy in the middle, which is kind of moderately complex and needs a kind of moderate amount of customization for different deployments, which are sort of in the middle in terms of the rate of learning. Okay, so that's everything on deployment-related cost reductions. I'm just going to kind of quickly talk about innovation-related cost reductions, because I think these are more intuitive in a lot of ways. So basically, as I said at the beginning, what an innovation means is it means the development of a new technology. And when this new technology is deployed, it will have its own experience curve. And we've seen this in different generations of energy technologies that we know about. So if we think about solar, the solar sector, concentrating solar, crystalline silicon solar, and thin film solar, they're all solar technologies, but they are different. They have different manufacturing processes. They work in different ways, and they have their own experience curves. The same is true for different battery chemistries and onshore and offshore wind. They have different experience curves. The point I wanted to make with wave energy here is that there are a lot of different potential ways that you can harvest wave energy. There are a lot of different potential wave energy converter designs out there, and they would absorb and convert wave energy in different ways. And they're fundamentally different technologies which would have different experience curves. When we start deploying wave energy at scale, we want to make sure that we're on the lowest experience curve possible. And that means that spending money on research and development and demonstration of different devices is important to make sure that we've kind of explored all the options and that we're deploying the best possible technology when we actually move to deploying it at scale. And to just kind of illustrate this with a diagram, imagine a kind of baseline experience curve for the wave energy sector. So you're starting at this cost, and then you're coming down the experience curve as the technology is deployed until you reach a point of cost competitiveness. And that blue area under the curve there, that represents the subsidy that's required to do that. However, if research and development and demonstration funding for wave energy devices resulted in the development of a better wave energy technology than that baseline curve, you'd be on this new lower experience curve. And that would require less subsidy to get you from the start point down to the point that your technology was cost competitive. Yeah, so that is kind of basically what my research was looking at for the wave energy sector. So I started by developing a kind of baseline potential experience curve for the wave energy sector, based on some kind of plausible assumptions from the literature. I then developed a model to evaluate the level of deployment, the time and subsidy associated with this deployment trajectory. And then I developed scenarios looking at the effects that innovation could have on these scenarios. And then finally made some kind of conclusions and recommendations based on this. So first of all, as I said, assumptions are needed to develop a kind of sensible baseline experience curve scenario for the wave energy sector. So the first thing I needed to do for this was identifying a kind of starting point for the experience curve. And that is the initial LCOE of early commercial wave energy deployments. So to do this, I looked at the literature to find LCOE estimates for where the wave energy sector might be when we start deploying kind of 10 to 20 megawatt arrays of the technology, corresponding to around 100 megawatts of global deployment. Generally, these cost estimates were kind of based on the most kind of established types of wave energy converter technology, so the kind of point absorber, surge type devices. Palamas comes up a lot just because there's good data available for Palamas, which researchers use in academic studies, and then also just some kind of studies from organizations like Ocean Energy Systems, which take responses from industry or wave energy experts about their prediction of where the sector will be in the future. And there's quite a range between these different studies in terms of the LCOE that they expect for these initial arrays of wave energy. So I basically chose 400 euros per megawatt hour because that intersects the range of a lot of these different studies. If you kind of look at this here, that's the cost on the y-axis, and you can see that 400 intersects quite a lot of them. So it seemed like a reasonable assumption to make. The second assumption was what the kind of cost target we're going for the wave energy sector. So I selected 100 euros per megawatt hour. Basically, that's similar to the target that Wave Energy Scotland uses. It's also similar to the most expensive forms of, as I said, fossil fuel generation in the UK, and also the most expensive low carbon energy sources, which is nuclear in the UK. It's about that as well. I selected a learning rate of 15% for this baseline scenario. Basically, that's because it's similar to wind energy, and it's also within the range of the other studies used in the literature. I think that's because wind energy is a much kind of more analogous technology to wave energy than something like solar PV, so it seemed like a more sensible learning rate to use. And then finally, I assumed a rate of deployment increase of 30% per year. Again, solar PV has seen a higher average deployment increase per year than that, about 35%, whereas wind energy is more like kind of 20% or just below that. So it seems like a kind of reasonable middle of the road assumption. Yeah, so I plugged all of these assumptions plus a few other ones into a model that I developed, which I'm not going to go into at all because in the interest of time. The output from this were some kind of potential, a kind of potential baseline cost reduction pathway for the wave energy sector based on that experience curve effect. So in these plots, the dark blue line is that baseline that I showed in the previous slide. Based on the assumptions in the previous slide. So we're starting at 400 euros per megawatt hour at 100 megawatts of cumulative deployed capacity globally. And then we're coming down that cost reduction curve to that target of 100 euros per megawatt hour. And under these baseline assumptions, that takes about 40 gigawatts of deployment globally and about 27 years. And that's even with a kind of relatively aggressive deployment rate. So it's not something that's going to happen overnight, at least based on the kind of assumptions I was using. You can see I've also plotted a kind of range of starting costs as well, basically because there's such a big range in the literature. I wanted to see what happened if you started below or above that. And you can see that it takes a bit longer and considerably more deployed capacity if you started at 500 euros per megawatt hour versus 400. Sorry, I'm going to get the hang of this before the end of the presentation. Yeah, and the thing that I've overlaid here as well in these kind of coloured shaded areas are the kind of approximate resource ranges in Europe and globally. And I think that's important to kind of highlight because you don't want to be producing a scenario where you have to deploy this much wave energy for it to be cost competitive when you're using up most of the resource in the entire world, because it would simply be completely unrealistic. But we can see in that baseline scenario, you're kind of comfortably below the resource that exists in Europe, even, never mind the whole world. Yeah, and the last thing that I looked at was evaluating the subsidy associated with these scenarios. So in that baseline cost reduction trajectory, it takes about 60 billion euros to subsidize your way down that experience curve. 60 billion euros, that might sound like quite a lot of money, and it certainly is. On the other hand, you've got to remember that that's spread out over almost 30 years, and also however many countries choose to deploy wave energy. It's not out of the realm that we've seen with other renewable energy technologies, for sure. I'm not going to dwell on this for too long, but this is the same plot, but looking at variation in the learning rate. So, as I said, it's 15% learning rate in the baseline scenario. And what I kind of want, which is similar to what we've seen in wind energy, what I want to kind of highlight here is that if wave energy had a very slow learning rate for some reason, which there's no reason to believe that it will, but if it did, that would be very bad news for the sector. You could end up with a really unrealistic amount of deployment being required. So I think this kind of just highlights that it's important to monitor the cost reduction trajectory that wave energy is on once it starts being deployed, and see if it is on one of these kind of faster learning cost trajectories, which hopefully it will be. Yeah, that's just the last couple of slides on this. So the last thing that I did was looking at the effect that innovation could have on these cost reduction pathways for wave energy. So I did this in collaboration with one of my colleagues at the University of Edinburgh, and we modelled additional pathways on lower experience curves. And this was to represent the effect that if there was a kind of better wave energy technology that was developed in that baseline cost reduction scenario through research and development, what effect that would have on the amount of deployment and cost to get down to that cost target. Really, these were meant to kind of represent plausible scenarios, not to quantify the effect that successful innovation could have. They weren't kind of based on a kind of specific wave energy innovation that we were looking at. And the kind of assumptions from these were based on technology development timescales, costs from the literature, and also ocean energy project databases. So some data that Wave Energy Scotland had, and also some stuff from the Cordis database. And yeah, I mean, we ran a lot of different scenarios, which again I'm not going to go into because they're difficult to explain in a short period of time. And ultimately, there was a similar finding from all the different scenarios that we looked at, which was that basically, if you can achieve a cost reduction through innovation before deploying a technology, the wave, before moving on to deployment in the wave energy sector, it can massively reduce the subsidy that's required related to deployment. So on the right-hand side of the screen here, you can see this is the subsidy associated with that baseline scenario, the 400 euro per megawatt hour scenario. Then these are some scenarios here where there is a 10% reduction in costs associated with innovation compared to that baseline scenario. And then these ones have a more ambitious 25% reduction in costs compared to that baseline scenario. And what you can really see here is that even that 10% reduction through innovation cuts your deployment subsidy by about a third, which is massive. So I think this just kind of really highlights that if further research and development and demonstration funding in the wave energy sector can lead to better technologies better performing technologies than I modelled in that baseline scenario, it would just massively cut the amount of deployment subsidy required to get it down to a cost competitive level. Okay, so that's me almost done. Just some kind of general thoughts from my work. I think the first thing is, that baseline scenario that I presented earlier, 60 billion euros in 30 years, it sounds like a lot of money and a lot of time. But to be honest, I think if we kind of assume those assumptions are realistic, it's not actually that bad. It's kind of comparable to what we've seen with other renewable energy technologies, and it's not something to be kind of scared about. However, the second point is that really if successful efforts into developing better technologies in that baseline scenario are achieved, then it would save a lot of the subsequent deployment subsidy. And I think wave energy is in a good position to do this because we're not yet kind of locked into one technology. There are lots of different options which we could, in terms of wave energy technologies that we could develop. I think the last point is that, I've talked a lot about the costs of deploying wave energy. We also need to think about what the kind of value of wave energy might be in a decarbonised energy system when we're thinking about how much it's worth spending on subsidising the deployment of wave energy. Because you could make arguments for it being kind of worth spending the same amount that we did on wind and solar, but also there are arguments you can make against that as well. So this is just my final slide. It's some kind of, reasons for kind of caution and optimism based on the work that I did. So starting off with caution for the wave energy sector so we can finish on a nice note. I think some of the enablers that have helped wind and solar go through that kind of massive cost reduction through deployment that they did might not be as applicable to the wave energy sector. So I think the first really obvious one is that when we were deploying wind and solar in the kind of early phases back in the kind of 90s and early 2000s, there weren't really many other good options in terms of low carbon electricity generation. You had nuclear, which was already kind of politically unpalatable at that point in a lot of places. So really, if you wanted low carbon electricity generation, you had to deploy wind and solar. For wave energy, we're not really in that position anymore. There are good alternatives for low carbon electricity generation. So that might be a kind of reason that we wouldn't want to spend as much money subsidising wave as we did on wind and solar. The second point, which I think is particularly kind of relevant to solar photovoltaic, is that technology benefited massively from a succession of things called niche markets. So these are markets which are less kind of cost sensitive than competing against kind of other large-scale power generators. So solar was initially deployed on satellites, and then moved to kind of consumer electronics and off-grid applications like weather stations, then went onto people's roofs, and eventually it got to the point that it's used as a large-scale kind of wholesale electricity generation technology. I'm not sure if that kind of nice succession of niche markets exists for wave energy. If people have kind of ideas about that, it would be nice to hear, but I can't see the same kind of nice progression that we've seen for things like solar existing for wave. The final kind of pessimistic point, I guess, is that while wave energy has a big resource, at least based on the resource estimates that I've looked at, it's considerably smaller than technologies like wind and solar. And that means the benefits of kind of enabling low-cost wave energy probably aren't as large as it has been with wind and solar. So that might kind of entail less subsidy being justified on its deployment. So that's enough of the pessimistic points, I think. In terms of some kind of optimistic ones now, we've seen that deployment-related cost reductions, the experience curve exists for these other technologies like wind and solar. And indeed, it's gone for an extremely long period of time. We've seen kind of an unbroken kind of cost reduction in both those technologies for like decades now. And we didn't know that would happen when we started deploying them, but I think that can give us confidence with the wave energy sector that there's no reason to believe that it won't follow a kind of similar cost reduction pathway. The second point is that, well, maybe wave doesn't need to get down to the same level of cost as these other renewable energy technologies. We've seen some kind of recent modelling looking at the tidal energy sector, for instance, showing that there's some significant system benefits in terms of when you're deploying it in a future energy system which is dominated by wind and solar, in terms of offsetting kind of expensive storage options. And that might be the same case for wave energy as well. I think for the UK as well, there's obviously a kind of economic opportunity from fostering a domestic wave energy market. We're in a very strong position regarding research and development into wave energy in the UK. We hold more intellectual property in wave energy than any other country, and we have kind of great testing facilities, so all the ingredients that you need to develop new wave energy technologies. And if we can support their early deployments as well, it might be something we could export to the rest of the world. Yeah, I think the kind of final point that kind of links up with the kind of research I was doing the rest of my PhD is I've seen an awful lot of kind of innovative wave energy technologies out there that could be developed if there was enough kind of funding in place. So I don't doubt that kind of breakthroughs could happen with sufficient support. Yeah, so thank you all for listening, and I'm happy to take any questions. Thank you.
Thanks very much. And gosh, I think for me, actually, what was fascinating there was looking at what happened with solar, and back in 1997, was it 1998, making those predictions that were. They were right, but it was 30 years later almost till we hit that sort of timelines that we're working on. I don't know if anybody's got a question. I've got some hands up straight away. Martin.
Wait for the microphone. I'm going to wait.
I was interested about your learning curve. You lumped everything together into one percentage, but that could come from experience from having thousands of devices and knowing what breaks and being able to avoid putting that bit into the component in the first place. It could just come from mass production because you've got machines that can make out 1 million of these every year instead of a man building 1,000. Have you looked into how that learning curve has evolved in the different types of technology? Because that surely is going to make a difference. as to what you may expect a learning curve for wave energy devices to be?
Sure, yes, that's a good question. I mean, it's some studies have looked at kind of trying to break out the different effects that contribute to experience curves or learning curves. Either phrase is used. It seems to be incredibly tricky to do, to be honest, and I think generally they do just kind of aggregate all of the cost reduction factors together and look at what the overall trend is. And yeah, the overall trend in something like solar PV has been a reduction of about 25% every time it's doubled in capacity for the last 30 years or so. Yeah, I think in solar, a lot of that has kind of come from improvements in manufacturing that's happened alongside deployment. Yeah, but it's a good question, and it's just something that is well, the literature seems to find very difficult to actually quantify the exact things that are going into the cost reduction. Sure.
Sorry. No, the reason I was asking the question was, if you're looking at what breaks and fixing it,
yeah.
Can you use models to get experience by building thousands of machines and running them at very low cost in a computer?
Well, I mean, that's a really good question. I'd imagine, well, it probably wasn't something that existed in the early stages of like wind and solar back in the kind of 90s, but nowadays that may well kind of accelerate the learning of a technology like wave energy now that we have better modelling tools. Yeah, it's a good point.
Okay, Neil and then Simon after Neil.
Yeah, thanks. Really just to help pick up on that last point Martin made about modelling. Yeah, you absolutely can do modelling the failures. However, you've got to know what it is you're trying to model. Mm-hmm. And so the experience at the moment is very, very thin. And so there's a real danger you come up with a great model that looks at one particular feature and then something else completely different fails. So I think the important thing is to gather experience, codify that, and model in parallel. Yeah. So it's not an either or, it's an and, I would say with that. Yeah,
that's definitely one of the things that's commonly cited in the kind of early development of wind energy was that or kind of testing laboratories like RISO in Denmark, they were gathering as much data as they could on the failure of wind turbines. You actually had to go and get your turbines kind of certified there before they could be bought, and yeah, using it to validate models. It was kind of cited as one of those things that was helped the Danish wind sector be so successful.
I think we'll take Simon, and then we've got an online question after that. Yeah.
First off, thanks for a really clear and interesting presentation. The other technologies that you showed the learning curves for, mm-hmm. By the start of the curve, they'd already pretty much converged. We knew what a solar panel looked like. We knew what a wind turbine looked like. Now, as we know, wave is not in that situation yet. So do you think that all the different wave technologies are already sharing a learning curve, or are they on separate parallel ones that may not fully contribute to each other as yet?
Well, I don't think wave energy is on a learning curve yet because it hasn't been deployed at scale. I think what will probably happen is generally if you go back to the very early stages of a sector's development, it's very messy and you can't really see a learning curve until a few hundred kind of megawatts of deployment. I think probably what will happen is there'll be some kind of convergence around the kind of best wave energy device, like one of those kind of topologies, or maybe a completely different one from the ones that I showed in the slide earlier will win out, and we'll have a learning curve for that technology. That's what I would expect. It's what's happened with things like solar and wind. Yeah.
Okay, thank you.
Okay, we got an online question?
Yeah, there was a question from Swain Hunter, but he's had to leave. So he put his question in chat, so I'll relay it for him. Are there any experience curves you're aware of for hydrogen production or as an energy storage medium?
Oh yeah, there definitely are for, I think, some early stage ones for electrolyzers, but I don't have them on the slides, and I can't remember what the learning rate is, so not too helpful. I guess the thing with hydrogen is you're always going to be, a driver of the cost with hydrogen is going to be the cost of the electricity you're putting into it. So the capital cost of your electrolyzer can come down, but a big component of it is going to be essentially the fuel cost, which is the electricity going into it, which is, if you want it to be green, it's going to be renewables. So yeah, it's kind of linked to the renewable energy cost reduction curves as well, the cost of hydrogen.
Neil, and then Neil had his hand up first. Yeah.
Yeah, thanks. A couple of points. One, you're spot on about the hydrogen side of things. About 60% of the cost of the hydrogen is likely to be the electricity. So your learning rate in the 40% is obviously going to be compressed. It's really a bit of an anecdote, really, for a bit of technical humility. One of the people who was involved in the Polaris machine was in a meeting in Department of Trade and Industry some years ago, and it was looking at a whole load of renewable technologies and what they should do and where they were going. And they talked about wind, and they talked about wave, and they were talking about offshore wind, and the question was raised about solar. And allegedly the civil servant heading the meeting slammed his hands on the table and said, "I am not talking about solar in this meeting. It is complete basket case. It'll only work for satellites. If anybody brings this up again, I'm shutting this committee."
Yeah.
And now, and that was probably about 2000 or so.
Yeah, but I think if you weren't aware that the learning rate was so steep for solar, I mean, it would have cost, I don't know, like the best part of €1,000 per megawatt hour back then, which would be crazy if you weren't expecting its cost to come down as it was deployed. So they probably just looked at what is the cost of solar now. And
yes, so my point is maintain your studies and keep at driving these points home, because just because somebody is sitting at the top of a desk doesn't mean they have perfect knowledge.
Mm-hmm. Yeah.
I actually have a few questions, but just building on top of that, I think what's interesting is even though solar did have that higher cost and it did have a steeper learning rate, is that actually it maybe the innovation curve that you were showing, maybe it doesn't shift down, maybe it starts much higher but has a much higher learning rate and therefore drops down, which is what we were seeing with solar. Although how would you ever know to then pick that one? And just related to that, I wondered whether one of the reasons, or if you've looked at the timeline of some of these technologies, how that impacts the learning rate. And there was something else related to that, but I can't remember what it was now. Just the actual cost of building the small scale. It's very easy to build small scale solar. It's not easy to build small scale wind. And I imagine it's the same with wave, and I just wondered if there was anything you'd looked at in your research on that.
Yeah. I mean, I guess that's quite a lot of questions.
Sorry, there wasn't more.
No, they're all good. They're all good questions. I mean, I think starting small in some ways is probably a good option, because it gives you that chance to kind of get demonstration and iteration in a period where it's not too expensive building a device that fails. I mean, we did see that with the wind energy sector. There was initially it did start very small, turbines of kind of tens of kilowatts being deployed for quite a long time. And there were a few kind of large-scale projects that kind of tried to bypass that gradual upscaling, and none of them kind of turned out to be particularly successful. You may have seen that to an extent with the wave energy sector. There was kind of funding put in place 10 years ago or so that was really targeting large-scale wave energy devices, trying to get them deployed as quickly as possible. And maybe we needed to take a more gradual approach of deploying more smaller devices, getting more kind of experience from demonstration before increasing the scale. What was the first question again?
It was more just pointing out the innovation curve. The learning rate for something that costs more now might actually be steeper.
Yeah. I mean, I guess you're right in saying we don't know what the rate of cost reduction is until we start deploying it. I guess there are some of those kind of in that plot, which I might not have explained very well, from which had reviewed a lot of different experience curve studies. There were some kind of general principles in there that super complex, kind of customized projects, the kind of, you think about kind of mega projects like nuclear, which are done kind of one time, they don't seem to demonstrate very much learning, whereas the kind of highly standardized technologies that are kind of churned out in factories, like solar PV and batteries, they seem to show a really strong learning effect. And there's also some other studies which have looked at scale, which have kind of shown that in general smaller scale technologies maybe have a kind of slightly higher learning rate than the super big ones. So it's possible there's some kind of learnings in there for the wave energy sector. Don't know.
Right,
Yeah.
There's been two hands up. I've got one at the back and then Rose wanting another question. I'll take one more after that if anybody's got one. If they don't, we'll end it there. So we'll take these two.
I do have a question, but just quickly to build on Neil's anecdotes, which I hadn't heard before. I'm sure you've seen this, Paul, but other people won't be aware. There was a graphic going around social media for a while showing the IEA, the International Energy Agency's projection of the cost of solar every year. And every year for about a decade, they predicted it was going to level out.
I think I actually have that in my slide deck.
Oh, do you actually have it?
I'll be able to find it. Oh no, don't bother.
Anyway, yeah. It was quite funny. But my actual question is going back to the 60 billion or thereabouts investment, or the 100 billion from Germany for PV, and of course the rest of us benefited then from cheaper PV. Did Germany get a return from that, or is it almost a first mover disadvantage?
I think for Germany it was a first mover disadvantage because towards the end of that time, China was manufacturing most of the PV. So I mean, they got a little bit of an advantage because Germany exported quite a lot of the manufacturing equipment to China initially, but now China has their own fully domestic industry, and Germany maybe manufactures kind of, I think it's kind of 10 to 20% of the solar panels that are in their country. So they probably didn't capitalize on that first mover disadvantage. So, but I think there are also some things we've learned about policy design for renewables since then. I mean, Germany had an uncapped feed-in tariff, so as many people could apply as wanted at a level. So I mean, they had 8 gigawatts deployed in 1 year at a level of over 500 euros per megawatt hour. It's insane, and that's for 20 years. So that's still on people's energy bills now. That's what you see if you're looking at the amount of renewable subsidy in your energy bills. It's not new renewables, it's stuff that was deployed a decade ago, really.
Thanks.
Yeah.
Just to make another point, you said Wave Energy Scotland were the sponsor of your degree. So Wave Energy Scotland's a really interesting example of a bit of clever government intervention. And if people don't know what happened, basically Wave Energy Scotland was set up and it went through, I can't remember the blooming initials, but basically it's a public procurement process. And it instead of providing grants to people to build a wave energy machine or come up with a different drive system or whatever, they came up with a public procurement model which basically said we will pay 100% for 10 different schemes, and out of those 10, 8 of them will go through to the next stage of the competition, and the next stage of the competition they then thinned it down to 6 and 4 and eventually got to 2. Both of those machines are being deployed in Orkney. One of them is sitting over in Garson at the moment, which is the AWS wave energy machine. The other one is the Motion machine, which was on the quay. I think it got lifted today. But the point is that by having that procurement process, they focused on fairly small deployments, which therefore were more affordable and were of a scale that could be managed. The alternative approach, which is one we've seen before, is that government seeks to pay for an electricity revenue. And the point there is that drives you towards building a big machine to get as much electricity and then maximise your revenue. As you go big, the costs go up, and the costs don't go up linearly. They go up in a horrible sort of curve. And also, to try and make sure you get your money back, you try and build these machines that last for 25 years. And the first machine in the water is supposed to last 25 years. Give me a break. So there's a real, I think Wave Energy Scotland did a really good job in terms of that procurement model to get activity going. I just hope Scotland's going to follow through with that now, because it's a critical stage when we need to move to the next, we need to build on all the investment that's been made so far.
Yeah, I think another kind of interesting thing about Wave Energy Scotland as well is, if I'm not mistaken, if the kind of IP that's generated by the companies that they work with, if it goes kind of unused, Wave Energy Scotland then gets access to it, which means that it's not wasted money, it's learnings that can be used for the sector in the future. And they've brought up stuff from kind of previous devices like Polamis as well, and that's a valuable resource for everyone now, so yeah.
Okay, last chance. Oh, we have one more question.
So a lot of what you've been talking about is the deployment rate and the cost involved in that subsidy. And so one of your last slides was showing what the change can be if it's a 10% reduction in that subsidy rate. But the question, I suppose, is how much research cost do you need to get to that point, which of course you can't necessarily answer, but maybe it's better to spend it on technology we already have just to get it deployed instead of waiting 27 years.
Yeah,
to be
that's a fair point. I mean, I think the actual costs of funding research and development and demonstration of projects is very low in comparison to the subsidy that you pay. So, I mean, something like Polamis received about I think it was under 20 million in public investment to take it from the start all the way to being a large-scale device. I mean, it crowded in kind of private investment towards the end, which might be a bit more difficult for Wave Energy nowadays, but it's small in comparison. I guess the thing is, there's the kind of success rate. It's how many projects have to fail before you get one that is actually a breakthrough, and we don't really know what that is. But I think it's a worthwhile thing to do, because you can do an awful lot of projects that fail and only one of them has to work, and it would still massively reduce the amount of deployment subsidy that would be needed. Of course, yeah, we do have cheap alternatives, and you might just say, well, keep on spending money on those instead. But I think personally it's nice to have a portfolio of different renewable energy technologies. I think that's important, because we don't know what's going to happen in the future.
This is going to be
So I'm just going to, once again, some context. 21 million for Polamis. We spend 28 million pounds a year on Marmite in the UK. Okay, that's one point. The second thing is, in terms
3 billion a year in nuclear decommission.
There you go.
3 billion.
3 billion.
Yeah.
There you go. Thanks everybody for chipping into that pot. And the other piece was in terms of the active R&D. So just, I'm going to shamelessly blow our own trumpet on this. So money was put into making EMEC happen, and it's been about 40 million pounds so far in what's happened. That R&D activity that we've done has shown a gross value add to the UK economy of 370 million pounds, of which 260 million is in Scotland, of which 120 million pounds is in Orkney alone. So the point is, the active R&D is of itself useful, and it does lead to things. And so, for example, the machine that's presently out on the tidal energy site by Orbital Marine Power will probably be doing around about 5 to 7% of Orkney's electricity at the moment. So that's the equivalent of basically us running one day a fortnight on tidal energy. Now, that R&D simply wouldn't have happened if money hadn't been put into the R&D activities that then lead to this. So the journey is useful as well as the outcome.
Okay, right. Thank you very much. Thank you.